So let's complete the remaining parts of exercise 2. So recall that this is how exercise 2 starts. X and y are any two real numbers. We have to prove that the greatest integer function satisfies some properties. So next, this is part D. We have already proved parts A, B and C. The greatest integer value of x divided by n equals the greatest integer value of x divided by n for any positive integer n. So as usual, we first solve this part and then we go to the other parts, and we start the solution like this. We already know that the real number x divided by n equals its greatest integer value plus another real number theta, which is non-negative and is less than 1. Okay. And then what we do, we multiply both sides of this equation by n, obtaining this other equation. The left hand side would become x and the right hand side would be n times this greatest integer value of x divided by n plus n theta. Alright. Now what we do, now with this information we consider the greatest integer value of x, and to carry out the calculation we are going to use part A. We will see what part A states here and what role it plays here. So the greatest integer value of x is the greatest integer value of this. Now part A says that if you are having something means some real number n theta plus an integer inside greatest integer function, that integer simply just comes out. Is this part an integer? Yes, n is already a positive integer and this is greatest integer, so this is also an integer, so the product is an integer. So that just simply comes out of this greatest integer function, leaving us with this one inside the greatest integer function. And then what we next do, then we divide this equation on both sides by n, obtaining this. Greatest integer value of x divided by n equals greatest integer value of x divided by n plus this greatest integer value divided by n. And now next we are going to use these inequalities to figure out what we can say about this part. The next part of the calculation will start like this. Also we have these inequalities. Theta is non-negative, that means theta is greater than or equal to 0 and theta is less than 1. We can multiply throughout by n. The inequalities will retain their direction because n is a positive integer. So that way we are next going to get 0. N times 0 is 0, that is less than or equal to n theta, which is less than n. Alright. Now next, what do we get from this? You see, 0 is an integer less than or equal to n theta. But by definition of greatest integer function, this value is the greatest integer less than or equal to n theta. So obviously this itself will be greater than or equal to 0. 0 is one such integer and this is the greatest. But of course, by definition again, this is the greatest integer less than or equal to n theta. So this is less than or equal to n theta, and n theta is already less than n. Now next we just simply forget this n theta and write these inequalities. That is 0 is less than or equal to this greatest integer value, which is strictly less than n. And then we divide throughout by n. Just like multiplying throughout by n does not affect the inequalities in the sense that the inequalities do not get flipped, dividing by n also won't have any such effect. So 0 will be less than or 0 divided by n is 0, that is less than or equal to this greatest integer value divided by n, which is less than 1. Now you look at these inequalities and you look at this equation. This real number is equal to an integer plus another real number, and that another real number is non-negative and less than 1. So by the definition of greatest integer function, this integer would be nothing but the greatest integer value of the left hand side. So that's how you have this identity proved. Next we have part E. Instead of calling it greatest integer every time, let us call it box. okay, box of nm divided by k, that should be proved to be greater than or equal to n times the box value of m divided by k, where n, m and k are any positive integers. This solution is very easy. We start with this inequality. The box value of m divided by k is by definition less than or equal to m divided by k. So we multiply both sides by n, which we can do, we can do means after multiplication the inequality retains its direction because n is a positive integer. So that way we get n times the box value of m divided by k less than or equal to nm divided by k. Now we concentrate on the box value of nm divided by k, which by definition is the greatest integer less than or equal to nm divided by k. However, this is some integer also less than or equal to nm divided by k. So the greatest nature of this makes it greater than or equal to that some other integer. And this is nothing but this, written slightly differently. So that's how we have the solution.